In this video, we'll look at a really important link between the thermodynamic equilibrium constant and the change in Gibbs energy under standard conditions. So this is incredible because this thing here links together the equilibrium chapters from before with the thermodynamics chapters from this past week or so. And the connection between them is really amazing, actually. So delta G we saw was equal to delta G standard plus RT natural log of Q, the reaction quotient. And we know that as a reaction proceeds, we can calculate G versus the reaction, and we'll find that G will bottom out at equilibrium. Okay, so at this point here, Q is equal to K. And delta G is equal to the slope of this graph. So we know that delta G is essentially equal to 0 at equilibrium. All right, stay tuned. So let's go ahead and calculate equilibrium. So delta G is 0 at equilibrium, so we can write the left-hand side as 0. That's equal to delta G standard plus RT natural log, reaction quotient. However, if we're at equilibrium, we know that the reaction quotient is equal to our friend, the equilibrium constant. So we can actually go ahead and rewrite this equation and write it as follows. Delta G standard is equal to minus RT times the natural log of the equilibrium constant. So this is the link to the past material here. So delta G that we now know how to calculate is exactly related to the equilibrium constant. We can actually rearrange this a little bit and get it in terms of, how do you calculate K from delta G? And we can do that by dividing both sides by minus RT. So we get natural log of K is equal to delta G standard over RT. And then if we want K, we can just anti-log. So that's e to the power. So that's e to the power of minus delta G standard divided by RT. So I'm going to put that in a cloud because that is a pretty amazing equation. So what are the implications of these two equations? So one implication is if delta G standard is very negative, which we saw is the sign of a favorable reaction, then the equilibrium constant will be extremely large. So if we plot what we mean by this, so if we plot G versus, say, the extent of the reaction Q, we see that if delta G standard is very negative, those are our pure reactants. Over here are our pure products, so they're much, much lower. So we can associate the gap here as delta G standard. Okay, and we can plot the curve, and what the curve does is it goes down and then just sneaks up at the very end. We can see the equilibrium point will be right here. So this is the equilibrium point. We can see when delta G standard is very negative, so the difference between the reactants in their standard conditions and their products in their standard conditions, when the products are much, much lower, the equilibrium lies very close to products. So K is exceptionally large. Now, conversely, when delta G standard is greater than 0, we're going to find that the equilibrium constant is going to be much smaller than 1. So we can plot the same curve here. So if we plot free energy versus the extent of the reaction, if delta G standard is greater than 0 or much greater than 0, that means that our reactants are here and our products are much, much higher. So delta G standard is simply this distance right here. If we plot the curve, what we find is that the curve looks something like that. So there's a little dip right here. So we essentially reach equilibrium at this point here. And we can see our equilibrium constant is very, very small, right? So it's very much smaller than 1, starts to get close to 0 perhaps. You might say, well, why does it go down at all? Well, it turns out that when you run the reaction, this is kind of neat actually, maybe beyond the scope of this course, you change reactants into products. And if you just convert 1 or 2 reactant molecules into products, then you get a heck of a lot increase in entropy. So you get an awful lot of microstates that suddenly appear, and that's quite favorable. So it turns out that you always get a little dip coming from mixing, but we see that it's not much of an effect here. So as we go over here, it's very, very unfavorable. So the mixing doesn't really do a lot for us here. So that's kind of cool, isn't it? So there's a link between K and delta G standard. I just think that's so fascinating. I think if you're going to get a tattoo, right, which, well, I'll leave it to you to decide whether you should or should not get. Delta G standard equals minus RT natural log K. this would be a great one to get. This would be a great one to put on your tombstone, I would say, as well. This is one of those top 10 equations in chemistry. That link, that ability to calculate delta G standard and have it tell you about the equilibrium constant is just mind-blowing. So we've done labs, right, where we've calculated the equilibrium constant by measurements, and it turns out that actually we didn't really need to do any of those labs at all. We could have just calculated from first principles from thermodynamics. So that's why thermo is amazingly powerful.